Far beyond our sun lies UY Scuti, a star so huge it seems to break the very rules of physics. Its size, its power, and its mystery challenge everything we know about the universe. Tonight we'll explore what makes this colossal star so extraordinary. If you enjoy cosmic journeys, please like, subscribe and share, and tell us in the comments, what would you name a star this enormous? Thank you for watching. Now let's begin. In a quiet reach of the Milky Way, where the galactic disk thickens into overlapping lanes of stars and drifting clouds, lies the small constellation called Scutum. Its name means the shield, and through its portion of the sky runs one of the densest bands of our galaxy's spiral arm. In this direction, the line of sight pierces thousands of light years of intervening gas and dust. Against this backdrop, a single red supergiant glows faintly to human instruments, invisible to the unaided eye, but commanding in its physical presence. This is UY Scuti, a star so large that even after careful revision by modern instruments, its estimated radius remains among the greatest ever measured. It rests within a rich stellar region about 5,000 to 10,000 light-years away, a distance still refined as new data accumulate. To find it is to look into a crowded depth, where faint reddened light must cross the thick interstellar medium before it reaches Earth. Through telescopes, the field around Scutum appears mottled with irregular streaks of darkness, where dust blocks starlight. Behind these layers, UY Scuti emits a dull orange-red glow, typical of a late-type supergiant. The star's outer light is scattered and softened by dust grains it has itself created, forming a faint halo that merges with the ambient glow of the Milky Way. The observation of such a distant object is an act of patience and precision. Astronomers rely on photometry to record subtle variations in brightness and spectroscopy to separate the light into its component wavelengths. These data reveal a cool surface temperature compared to smaller, hotter stars around 3,000 degrees Celsius, gentle by stellar standards, but still thousands of times hotter than any furnace on Earth. Its luminosity, the total energy radiated per second, far exceeds that of the Sun, shining hundreds of thousands of times brighter, even as much of its radiation escapes in the infrared unseen to human eyes. The region around UY Scuti forms part of the Scutum Centaurus arm, one of the Milky Way's major spiral structures. This segment of the galaxy is rich in massive star clusters and regions of active star formation. Dust lanes and molecular clouds stretch across the foreground, masking distant light, and causing reddening, a process in which shorter wavelengths are scattered more strongly, allowing the longer red wavelengths to dominate. As a result, the visible colour of UY Scuti to observers is deeper and richer than it would be if seen without interference. The same effect that tints sunsets on Earth's horizon shapes our view of this immense star across thousands of light years. The constellation Scutum itself is modest, defined by a small pattern of faint stars that trace no strong figure. Yet astronomers value it as a window into the inner regions of the galaxy. Through this area, telescopes can glimpse the great star clouds of the Sagittarius arm and the central bulge beyond. UY Scuti resides in this direction, surrounded by other supergiants and luminous blue stars, forming a scene of quiet extremes. The presence of such a massive star indicates that the region once contained dense clouds of hydrogen capable of birthing giants. Though UY Scuti now nears the end of its life, it belongs to a stellar generation that transformed primordial gas into heavier elements and released them into space through steady outflow. When first catalogued, UY Scuti was not immediately recognized as extraordinary. It appeared as a variable star whose brightness changed over periods of several hundred days. This variability, detected through repeated observations, marks it as a semi-regular pulsating supergiant. Such stars expand and contract in cycles, changing both temperature and luminosity. Early measurements in the 20th century placed it among the largest known stars, suggesting a radius thousands of times greater than the Sun's. With improved instruments like the Gaia spacecraft, which refines distance estimates through precise parallax measurement, newer data have revised its scale downward. Even so, its diameter remains immense, encompassing a volume that could contain the Sun and the orbits of the inner planets many times over. Its apparent brightness from Earth is modest, because much of its energy is radiated at wavelengths absorbed by dust or invisible to the naked eye. The act of observing UY Scuti from Earth is influenced by the limitations of the atmosphere and the tools used. Ground-based telescopes capture its light through air that shifts and trembles slightly, distorting measurements. Infrared detectors both on Earth and in space help bypass this limitation by recording radiation that penetrates the dust. The European Space Agency's Gaia mission, designed to map stellar positions and motions with exquisite precision, has been essential in recalibrating our understanding of distances in this crowded galactic region. Its data suggest that earlier estimates may have overstated UY Scuti's scale, though even reduced values preserve its standing as a remarkable supergiant. The ongoing process of refining such data illustrates how measurement in astronomy evolves not by revelation but by incremental clarity, one data set correcting the next. Beyond its physical statistics, UY Scuti's presence embodies a late stage in stellar evolution for massive stars. It has expanded enormously as nuclear processes in its core have altered its internal balance. Hydrogen fusion has largely ceased in the core, replaced by fusion of heavier elements in surrounding shells. The result is a swollen outer envelope, cool and diffuse compared with its earlier, more compact state. This transformation is typical of red supergiants, which occupy the final phases before catastrophic collapse. Yet for now, UY Scuti endures, releasing part of its outer material in slow winds that form a faint envelope. In images taken with sensitive infrared instruments, this surrounding material glows softly, evidence of the star's constant exchange with its environment. Looking towards Scutum on a clear night, even though UY Scuti cannot be seen directly without aid, one might imagine the quiet magnitude hidden behind the dark dust lanes. Each photon that reaches an Earth-based detector has travelled thousands of years through the galactic plane, passing through clouds, magnetic fields and drifting grains before finally registering as a point of data. It is a subtle bridge between an immense physical process and human perception. The constancy of its light across time, though varied by cycles of pulsation, connects the vast with the minute, the energy of fusion with the faint signal recorded on a sensor. The observer's role is to measure without exaggeration, to trace patterns of brightness and motion that reveal not grandeur but structure. In this first view of UY Scuti, the star remains distant, a point within a complex galactic panorama. Around it, countless other suns populate the Scutum Centaurus arm, each at a different stage of life. Some are forming within dusty nurseries, others have already dispersed their envelopes into the surrounding medium. The quiet coexistence of creation and decay defines the region's character. Between Earth and UY, Scuti stretches a crowded and uneven corridor of the Milky Way. The region through which its light travels is dense with stars, clouds of hydrogen, and drifting sheets of interstellar dust. Each layer along the line of sight alters the starlight, slightly scattering and absorbing parts of the spectrum, bending the light through fine grains suspended in space. Observers describe this as extinction and reddening. The more dust between the observer and the source, the dimmer and redder the star appears. In the case of UY Scuti, this reddening is considerable. Its light must cross a thickness of the galactic plane rich in cold material, turning the star's original orange glow into a deeper muted red by the time it reaches Earth. For astronomers, understanding this line of sight is essential, because every observation of UY Scuti carries with it the influence of everything between. The Milky Way's disk, though delicate in appearance, is not transparent. Photons leaving the surface of the star are absorbed and re-emitted countless times by interstellar grains, before a tiny fraction finally emerges clear enough to be detected. Mapping these obstructions is as important as measuring the star itself. In the direction of Scutum, several layers of dust clouds and nebulae obscure the galactic core. Instruments tuned to visible light reveal only patches of brightness scattered among darker lanes. Infrared telescopes able to pierce much of this obscuration show that the space behind is crowded with distant clusters and luminous sources. UY Scuti's position places it slightly beyond several known star-forming complexes within or near the region, associated with the Scutum Centaurus arm. This arm is one of the major spiral structures of our galaxy, wrapping inward toward the centre and containing a mix of old red supergiants and newly formed blue giants. It is a dynamic part of the Milky Way shaped by density waves that compress gas and trigger the birth of stars. UY Scuti may once have formed in such a cluster, though any association has long since dispersed as stellar motions carried its siblings away. The cluster's memory remains only in the composition of the star's atmosphere, which retains the chemical signature of its birth environment. When astronomers observe along this galactic corridor, they must account for the distance and distribution of intervening matter. Surveys of interstellar hydrogen using radio wavelengths trace vast sheets of neutral atoms that absorb and emit radiation at a characteristic frequency. These maps show that the region between Earth and Scutum is layered with alternating concentrations of gas, suggesting pockets where starlight dims abruptly. Optical and infrared extinction maps further refine this picture, showing where dust accumulates in filaments and clumps. UY Scuti's line of sight passes through several of these zones. The cumulative effect of this material is to reduce the star's apparent brightness by several magnitudes, meaning it appears hundreds of times dimmer than it would if observed in open space. Yet even with this dimming, the star's inherent luminosity remains vast enough to register clearly in infrared bands. The Milky Way seen in this direction lies edge-on, so our view through Scutum is effectively a cross-section of the galactic disk. Stars overlap at every distance from those only a few hundred light-years away to those more than 10,000. Distinguishing which ones belong to the same structure requires precise measurement of parallax, the small apparent shift in position that occurs as Earth moves around the Sun. For a star as distant as UY Scuti, this shift is tiny, amounting to only fractions of a millisecond. Instruments aboard the Gaia spacecraft detect such displacements, with extraordinary accuracy allowing astronomers to refine the star's estimated distance. These measurements not only reduce uncertainty about UY Scuti itself, but also help chart the shape of the Milky Way's inner arms. Each new revision to the data slightly changes our understanding of how far away the star is, and by extension how large it appears to be. The star's surrounding neighbourhood is not empty. Nearby, in the same region of space, lie other evolved red supergiants, each shedding mass into the surrounding medium. Their collective outflows enrich the local interstellar environment with dust grains composed of silicates, carbon, and metallic oxides. Over time, these materials drift outward, cooling and coagulating into complex shapes that later become part of new stellar systems. In this way, the region around Scutum functions as both a graveyard and a nursery recycling material between generations of stars. The diffuse emission detected by infrared observatories often includes contributions from multiple sources overlapping along the line of sight, so disentangling which part belongs to UY Scuti demands careful spectral analysis. Scutum's portion of the galaxy also contains several well-known objects used as reference points for calibration, such as the open cluster NGC 6664 and the rich star-forming region of W43. These landmarks allow astronomers to compare distances and extinction values, building a layered three-dimensional picture of the galactic structure. UY Scuti sits beyond many of these markers, which means its light carries the imprint of nearly every intervening feature. When its spectrum is spread into a rainbow of wavelengths, the telltale absorption lines of interstellar sodium and calcium appear fingerprints of the clouds it has crossed. The depth and shape of these lines reveal the cumulative density of the medium between the star and the observer. In this way, studying UY Scuti also teaches us about the Milky Way itself. To comprehend the vastness of this environment, imagine the light leaving UY Scuti today. It travels for thousands of years before reaching Earth. During that journey, entire civilizations rise and fall, yet the photons continue untouched by the passage of human time. Along the way, they interact with interstellar dust. Some absorbed, others scattered into new directions. The faint reddish glow that finally arrives at the detector is the sum of all these interactions. Astronomers correct for these effects mathematically, but each correction carries uncertainty. Small errors in distance estimation or extinction can translate into large differences in derived size and luminosity. This is why the numbers describing UY Scuti, its radius, brightness and mass, have changed repeatedly over the years. Each revision reflects not confusion, but improved clarity, a refinement of the line of sight itself. The structure of the galactic plane near Scutum is dynamic. Massive stars like UY Scuti blow bubbles in the surrounding medium, pushing gas aside and creating cavities. Supernova remnants from previous generations ripple through this environment, stirring it with shock waves that compress some regions and disperse others. Over millions of years, these processes reshape the arm's structure. The gas density fluctuates, forming bright emission nebulae, where ultraviolet light from young stars excites the gas. Against this active background, UY Scuti's calm red glow is easy to overlook, yet it represents a stage of stellar evolution, far older than the blue stars nearby. Its presence alongside them highlights the continuous cycle of birth and decay that defines the Milky Way's interior regions. Even the motion of UY Scuti through space adds complexity to its environment. Spectroscopic measurements of its radial velocity show that it drifts relative to the Sun at a speed of several tens of kilometers per second. This movement, combined with the gravitational rotation of the galaxy, means that over tens of millions of years its position within the Scutum arm will shift. The dust and gas it emits will mix with the surrounding material, contributing to the next generation of molecular clouds. Thus, the line of sight that now connects Earth and UY Scuti is temporary. The distribution of matter between will change as stars move gas flows and new clouds condense. The Milky Way's spiral pattern, though majestic in scale, is not fixed. It is a living structure in constant motion. Through this layered and evolving neighbourhood, UY Scuti's light continues its slow passage. Every observation captures not only the star but the story of its surroundings, the scattering grains, the intervening gas, the faint background of countless other suns. To measure the brightness of this single red point is to trace the structure of an entire arm of the galaxy. It is through understanding the complexity of this path, the line of sight from the shield-shaped constellation to our telescopes, that astronomers are able to isolate the true properties of the giant itself. Beyond the haze of dust and the crowd of neighbouring stars, UY Scuti persists, steady in its luminosity, a constant signal crossing the mutable fabric of the Milky Way. The light that reaches Earth from UY Scuti is more than a simple glow. It is a coded message about distance, temperature and size. For centuries, astronomers have relied on such light to measure the depths of space, long before spacecraft or parallax data made precision possible. The faint red-tinted radiation of UY Scuti carries within it subtle variations that allow experts to estimate its position within the galaxy. The process begins with photometry, the measurement of brightness through different filters. By comparing how much light the star emits at various wavelengths, observers infer its intrinsic luminosity and the extent to which dust has dimmed its signal. Spectroscopy then separates that light into fine bands, revealing absorption lines that correspond to elements in both the star's atmosphere and the interstellar medium along the path. Together, these techniques form the foundation for determining distance in astronomy. Measure brightness, correct for extinction, and compare the result to what is expected from a star of known type. UY Scuti's classification as a red supergiant of spectral type M has long indicated a cool extended atmosphere and high intrinsic brightness. Early distance estimates placed it nearly 10,000 light-years away, yielding a calculated radius that made it appear larger than almost any other known star. These values were drawn from ground-based observations which depended on uncertain calibrations of nearby variable stars and assumptions about interstellar absorption. The advent of space-based astrometry changed that. When the European Space Agency's Gaia mission began mapping the Milky Way, its precision transformed our understanding of stellar distances. Gaia measures parallax, the tiny annual shift in a star's apparent position as Earth moves around the Sun. For nearby stars, this shift is easy to detect, but for distant supergiants like UY Scuti, it is minute, measured in thousandths of an arc-second. Yet even such a small displacement, observed with the sensitivity of modern instruments, allows astronomers to revise earlier estimates by large factors. Gaia's data reduced UY Scuti's likely distance, suggesting it may be closer than once thought, perhaps around 5,000 to 6,000 light-years. The corresponding adjustment to size followed immense still, but no longer beyond all theoretical limits. This refinement illustrates the evolving nature of measurement. In astronomy, numbers are not permanent, they are approximations awaiting correction. Each new generation of instruments tightens the range of uncertainty. The star remains among the largest known, yet its true extent now fits more comfortably within physical expectations for a late-stage red supergiant. What appeared once as an object that defied known physics now aligns with the upper envelope of stellar models. This does not diminish its scale. It remains vast beyond comprehension, but it situates UY Scuti within the continuum of stellar evolution, rather than outside it. The revision also highlights the importance of cross-checking methods. Parallax, though direct, can be affected by motion within the star's extended atmosphere, or by variability that shifts the apparent center of light. Combining Gaia data with spectroscopic velocity measurements and infrared photometry helps reduce such errors. Light behaves differently depending on the wavelength through which it is observed. Visible light from UY Scuti is strongly dimmed by dust, but infrared wavelengths penetrate that dust more effectively. Observatories operating at these longer wavelengths, such as those using the Very Large Telescope and other infrared arrays, detect a brighter signal and reveal structures near the star that cannot be seen in optical bands. These observations also confirm the presence of circumstellar dust, a veil of particles produced by the star's own outflowing material. The mixture of dust and gas surrounding UY Scuti both absorbs and re-radiates energy, contributing to its complex brightness profile. By modelling this interaction, astronomers refine estimates of total luminosity and distance simultaneously. It becomes an iterative process measure the light correct for extinction test against models and repeat until consistency emerges. The history of determining distance to UY Scuti mirrors the broader story of astronomical progress. In the mid-20th century, variable stars like Cepheids and Mira-type pulsators were used as standard candles objects whose periodic changes in brightness could be correlated with intrinsic luminosity. By comparing apparent and absolute brightness, distance could be inferred. UY Scuti, though semi-regular rather than strictly periodic, was initially studied through this approach. Observers recorded its fluctuations over months and years, noting cycles of dimming and brightening caused by slow pulsations of its outer layers. However, without precise knowledge of interstellar extinction, the results remained uncertain. Each observer derived slightly different distances, and the radius derived from those distances varied accordingly. The more precise Gaia data now anchors these earlier relative methods, providing a firm baseline upon which to build. Distance is more than a number. It defines scale, luminosity, and physical reality. A small change in estimated distance for a star of such brightness can double or halve its apparent size. For UY Scuti, the difference between 8,000 and 5,000 light-years translates into a substantial shift in calculated radius. That change alters the inferred temperature distribution and even the estimated mass loss rate. In this way, one parameter affects many. The precision with which light is interpreted becomes the key to understanding the star's physical nature. Even now, researchers continue to analyze the Gaia data, adjusting for potential systematic errors caused by crowding in the dense galactic plane. In such a field, even small neighboring stars can influence the parallax solution. Each correction brings the picture of UY Scuti into sharper focus, though some uncertainty will always remain. Beyond measurement, the behavior of light itself offers clues about the structure of space between Earth and the star. As the waves pass through the interstellar medium, some frequencies are absorbed by specific atoms, leaving narrow, dark lines in the spectrum. By measuring the shift and depth of these lines, astronomers map the distribution of gas along the line of sight. They can determine where dust clouds lie and how fast they move relative to the Sun. For UY Scuti, multiple absorption components appear, indicating several layers of material at different distances. This pattern confirms that its light passes through a thick stratified region of the galactic disk. Each layer subtracts a fraction of brightness, producing the heavy reddening characteristic of this direction. Correcting for these effects requires careful modelling, but once done, the intrinsic colour and luminosity of the star emerge. Light is the only messenger that reaches us directly from UY Scuti. No spacecraft has visited it. No parallax can be seen with the naked eye. Yet from that faint signal, human instruments reconstruct the entire geometry of the system. The star's apparent magnitude, color indices, and spectral profile are transformed through mathematics into distance, temperature, and energy output. In the language of astronomy, photons become measurements, and measurements become understanding. The faint beam that travels thousands of years through darkness becomes a numerical statement about the scale of a dying giant. As technology improves, these measurements will tighten further. Future missions designed to map the Milky Way in infrared and radio wavelengths will pierce the remaining uncertainty caused by dust. They will refine parallax data for distant supergiants and test models of stellar evolution at the upper limit of mass and radius. For UY Scuti, this means its estimated size may continue to change slightly, but its position as a benchmark among red supergiants will remain. The light that reveals its distance also traces the methods by which humanity measures the universe: slow, careful and cumulative. Each observation adds one more layer of certainty to a structure built entirely from photons that began their journey before recorded history. In the quiet precision of such work lies the measure of both the star and its observers. UY Scuti's light crossing the Milky Way dims and reddens, scatters and recombines, until a faint signal reaches the instruments orbiting Earth. In that signal is a record of distance, a time capsule carried on a beam of radiation that began when early civilizations were just emerging. The path it followed across the galaxy now allows the human eye, aided by technology, to gauge the true scale of one of nature's vastest creations. The distance is no longer an abstraction. It is the space through which this light has passed, the silent corridor of stars and dust that separates our small world from the immense furnace of UY Scuti. When astronomers describe UY Scuti as one of the largest known stars, the statement carries layers of qualification. Size in astrophysics is not a fixed surface, but a measure that depends on wavelength transparency and method. A red supergiant like UY Scuti has no sharp edge. Its outer layers fade gradually into space, merging with the wind that constantly escapes from it. Still, comparison gives shape to the concept. Even with the reduced radius implied by modern distance data, the star remains extraordinary. If placed at the center of our solar system, its photosphere would stretch far beyond the orbit of Mars, perhaps approaching or exceeding the orbit of Jupiter, depending on which observational band defines its boundary. This imagined scale, though approximate, situates the object within a frame the human mind can grasp. The Sun, in comparison, would appear as a small point engulfed by an ocean of glowing gas. The surface of UY Scuti is not solid or even stable. It consists of huge convective cells that rise and fall in cycles lasting months, each cell potentially larger than the entire orbit of Earth. From space, its appearance would not be smooth but mottled, dimly bright in patches where hot gas wells upward and cooler regions sink back toward the interior. To understand its rank among the giants, astronomers compare UY Scuti with other extreme red supergiants, such as VW Canis Majoris, W. Cephei, and Stephenson 218. Each represents a late evolutionary stage of a massive star with radius estimates that depend on distance and method. Stephenson 218 currently holds the record for largest known radius based on revised measurements suggesting more than 2,000 times that of the Sun. UY Scuti, after adjustment, lies somewhat below that, but still comfortably within the upper percent of known sizes. These comparisons are not contests, but calibrations of models describing how stars expand as they approach the end of nuclear fusion. The limits of such expansion are governed by physics, radiation pressure pushing outward, balanced by gravity pulling inward. A star like UY Scuti teeters near this equilibrium so extended that its surface gravity is barely strong enough to hold its outer layers. The consequence is a steady, gentle outflow of material, forming a circumstellar envelope that dims and reddens its light. The idea of size for such an object is abstract. The photospheric radius is defined as the distance from the center at which the star becomes opaque to visible light, but because opacity changes with wavelength and temperature, different instruments record slightly different values. Infrared observations tend to see deeper, revealing a smaller effective radius, while visible light measures the cooler outer regions. The difference can be hundreds of millions of kilometers. This variability explains why earlier estimates of UY Scuti's size appeared to defy the limits of known physics. At greater assumed distances, and with optical measurements biased by dust, its radius seemed to exceed even the most extreme theoretical models. As precision improved, the numbers settled into a range consistent with other red supergiants of similar mass and temperature. The correction did not reduce its significance, it refined it. The star remains immense, luminous and instructive, offering a living example of how stellar envelopes behave near the threshold of gravitational stability. Scale also concerns luminosity. UY Scuti radiates tens of thousands of times more energy than the Sun, though its surface temperature is less than half as hot. The difference arises from its sheer size. A cool object can emit enormous total energy if it possesses an equally enormous surface area. In physical terms, the star converts energy from its core into outward radiation, which must diffuse through vast distances of convective layers before escaping into space. The journey of a photon from the core to the surface may take tens of thousands of years, bouncing through dense plasma before reaching the photosphere. By the time it leaves, the energy is spread across a wide spectrum dominated by red and infrared light. To an observer, this results in the soft, ruddy glow characteristic of late-type supergiants. When comparing UY Scuti to other objects, the difference between apparent and absolute brightness becomes crucial. From Earth, the star appears faint because its light is filtered through thick interstellar dust. Yet after correcting for that obscuration, its true luminosity places it among the brightest known stars of its type. By contrast, hotter and more compact stars, blue supergiants and Wolf-Rayet stars may outshine it in total energy output but not in physical size. The distinction between brightness and dimension often leads to confusion. A small, extremely hot star can appear brighter than a huge cool one. The two properties are not directly linked. UY Scuti exemplifies this separation: immense in volume, gentle in colour and modest in apparent magnitude. The concept of comparing such stars also extends beyond simple numbers. Each of these massive supergiants represents a different balance of mass, age and internal chemistry. VY Canis Majoris, for example, exhibits violent mass loss and an irregular nebula of expelled gas, while UY Scuti's outflow appears steadier. RW Cife shows semi-regular pulsations similar to UY Scuti, suggesting that their outer layers respond to internal cycles of fusion and convection. Stevenson 218, residing in a rich cluster, provides a context for environmental influence. Studying these stars together helps astronomers test how metallicity and initial mass determine the end stages of stellar evolution. In this framework, UY Scuti occupies a central position: massive but not extreme variable, but not chaotic shedding matter slowly into its surrounding dust shell. If the solar system were placed beside such a star for comparison, its scale would vanish into insignificance. The Sun's diameter is about 1,400,000 kilometers, while UY Scuti's may approach 2 billion. The contrast is difficult to picture. Even the distance from Earth to the Moon, nearly 400,000 kilometers, would fit easily within one small fraction of its radius. The light crossing its diameter would take more than an hour, while the same light crosses Earth in less than a second. Yet the star's density is low. Its average material is far thinner than air. If one could somehow immerse a spacecraft within its outer atmosphere, it would not crash or burn instantly, but drift through tenuous gas, heated and ionized, yet extremely diffuse. The visual impression, if such an encounter were possible, would be one of vast emptiness illuminated from within by deep red light. The notion that such an enormous structure can remain coherent arises from the balance of internal energy and gravitational force. In the core, fusion reactions of helium and heavier elements release energy that pushes outward. Gravity acting on the star's mass draws inward. At equilibrium, the two forces sustain a stable radius. For red supergiants, this balance is delicate. Small changes in core pressure or mass loss rate can cause the outer layers to expand or contract measurably, leading to the observed semi-regular variability. In this sense, UY Scuti is not static. Its scale fluctuates over months or years, breathing in slow rhythm. Each expansion cools the surface slightly, each contraction warms it, producing gentle oscillations in brightness. Comparisons of scale between red supergiants serve not to crown a single record holder, but to test the physical laws governing stellar structure. The equations describing hydrostatic equilibrium, radiative transfer, and mass loss predict an upper limit beyond which a star would lose its outer layers faster than they could be sustained. Observing objects like UY Scuti helps refine that limit. Its measured properties lie close to the theoretical boundary, confirming that nature operates near the extremes allowed by physics, but not beyond them. In this way, what once seemed to defy the limits of physics becomes a validation of those limits expressed through the calm persistence of a star nearing its conclusion. The perspective of comparison extends to time. While the Sun will persist in relative stability for billions of years, a massive star like UY Scuti burns its fuel quickly. Its entire lifespan may span only a few million years, and its present red supergiant phase represents a tiny fraction of that duration. Against the scale of human history, this seems eternal. Against cosmic time, it is a fleeting episode. Yet during that brief interval, the star's scale ensures its influence. The material it expels into space will seed future clouds of gas and dust, contributing to the ongoing cycle of creation within the galaxy. Its scale is not just spatial, but generational, a measure of its role in shaping what comes after. Among the bright gatherings of Scutum UY, Scuti remains a point of quiet enormity. Even as telescopes refine its measurements and reduce its former exaggerations, the essential truth endures. It is a giant among giants, occupying a size range where matter itself approaches the edge of stability. In calm light, it continues to affirm both the vastness of nature and the precision of the tools that allow such vastness to be known. Surrounding UY Scuti is a faint extended haze that marks the boundary where the star's material leaves its surface and merges with interstellar space. This is the outer dust shell, a diffuse envelope formed by centuries of mass loss. In such a region, gas expelled from the star cools as it expands, allowing molecules and tiny solid grains to condense. Silicates, aluminum oxides, and other compounds solidify from the wind and begin to drift outward, driven by radiation pressure from the immense luminosity within. The dust shell does not shine brightly in visible light. Instead, it glows softly in the infrared detectable, only to sensitive instruments that measure heat rather than color. To the human eye, it would appear as a dim, diffuse cloud surrounding an almost invisible point blending into the general glow of the Milky Way. This layer is not uniform. Observations suggest that the material flows unevenly, shaped by variations in the stellar wind and by the star's slow pulsations. In some directions, dense clumps form as ejected gas cools and dust grains coagulate. In others, the outflow remains thin and transparent. Over decades, these patterns shift as new material joins the flow, and older matter drifts farther away. The dust shell is therefore both a record and a process. It preserves traces of the star's past behavior while continuing to evolve in real time. Each grain of dust represents atoms forged deep inside UY Scuti's interior, carried outward through layers of gas and finally released into space. Once freed, these particles will eventually join the general interstellar medium, contributing to the raw material from which future stars and planets will form. The formation of dust in such an environment depends on temperature and density. Near the photosphere, gas is too hot and thin for molecules to survive. As it expands outward, the temperature falls below the condensation threshold, allowing complex compounds to assemble. Radiation from the star then exerts pressure on the dust, pushing it outward in a slow wind. This coupling between radiation and matter creates a self-sustaining outflow. As more dust forms, more material is driven away, which in turn reduces the surface density and allows additional cooling. Over time, this process removes a measurable fraction of the star's mass. Estimates of the mass loss rate for UY Scuti suggest that it sheds roughly a 10,000th of a solar mass each year, a rate sufficient to strip several suns' worth of material over its remaining lifetime. The dust shell thus represents the outer expression of a continuous transformation, where matter once bound by gravity becomes part of the galaxy's wider circulation. Infrared surveys reveal that this envelope extends several thousand astronomical units from the star distances comparable to the outer boundaries of our solar system. Within that volume, gas and dust coexist at temperatures of only a few hundred degrees Celsius, cold enough for molecules such as carbon monoxide and water vapor to persist. These molecules absorb and emit radiation at characteristic wavelengths, which astronomers use to map the structure and motion of the shell. By examining the Doppler shifts of these spectral lines, researchers can determine how fast the material moves and in which directions. The results show a slow but steady expansion with velocities of a few tens of kilometers per second. This flow carries the outer layers of UY Scuti outward into the surrounding interstellar medium, forming a tenuous cocoon that drifts through the galactic arm. The interaction between this expanding shell and the interstellar environment shapes the immediate neighborhood of the star. As the outflow encounters ambient gas, it creates a faint shock front, compressing and heating the material ahead. Over thousands of years, this boundary moves outward, gradually dispersing into the background medium. The density of dust decreases with distance, but even far from the star, traces of its material persist as an infrared echo detectable by sensitive space telescopes. In images taken by these instruments, the region appears softly luminous, with the central star surrounded by concentric halos of cooling dust. Each halo corresponds to a phase of enhanced mass loss, perhaps tied to variations in the star's pulsation cycle. The pattern provides a chronicle of the star's history, written not in words, but in light and temperature. The composition of the dust also carries information about the physical conditions near the star. Spectra show features associated with silicate grains, particularly those containing magnesium and iron. These materials form under oxygen-rich conditions consistent with the chemistry expected in a red supergiant's atmosphere. Some carbon-bearing molecules are present as well, though in smaller amounts, suggesting that the balance between oxygen and carbon remains tilted toward the former. The presence of crystalline silicates indicates that parts of the outflow cooled slowly enough for atoms to arrange into ordered structures rather than amorphous glassy forms. Each type of grain reflects the temperature and density at its birth, providing a record of the microscopic environment within the wind. The outer dust shell of UY Scuti also plays a role in regulating how the star appears from afar. By absorbing and scattering radiation, it dims the visible light and re-emits it at longer wavelengths. This reprocessing shifts much of the star's energy output from the optical into the infrared, altering its apparent color and brightness. The same mechanism that hides its true brilliance from human eyes ensures that it cools efficiently, preventing runaway heating of its outer layers. In effect, the dust shell acts as both veil and valve, concealing the star's radiance while mediating its energy loss. The resulting balance allows the extended atmosphere to remain stable over timescales of many centuries despite constant mass loss. The shape of the shell hints at internal asymmetry. High-resolution observations with interferometers reveal slight elongation and uneven brightness signs that the outflow may not be perfectly spherical. Localized convection on the stellar surface could eject material preferentially in certain directions, creating arcs or plumes. Magnetic fields, though weak compared with those of compact stars, may also guide the flow. These irregularities remind astronomers that such a star is not a simple sphere but a dynamic system, where gravity, radiation and turbulence interact across immense distances. The dust shell records these interactions as subtle patterns in its distribution, each reflecting the hidden forces at work beneath the glowing surface. From a galactic perspective, UY Scuti's dust shell contributes to the chemical enrichment of its surroundings. The heavy elements locked within the grains, silicon, magnesium, iron and oxygen, will eventually mix into future molecular clouds. When those clouds collapse to form new stars, the material from UY Scuti will become part of new planetary systems, continuing the cosmic cycle of creation and decay. This process is fundamental to the evolution of galaxies. Without the contributions of red supergiants, the universe would lack many of the solid materials essential for rocky planets and life. Each grain drifting from UY Scuti thus represents a small but significant addition to the fabric of the cosmos. The outer dust shell also serves as a preview of the star's eventual fate. As the mass loss rate increases in its later stages, the envelope will thicken and expand, perhaps forming a more complex nebula. When the core finally collapses in a supernova, the shock wave will sweep through this shell, heating and compressing it into intricate filaments of glowing gas. For now, however, the system remains quiet. The shell expands slowly and the star continues to radiate with steady brilliance. Its appearance is serene, almost static, yet beneath that calm lies constant motion, a wind of particles invisible to the eye but shaping the space around it. To observers, the outer dust shell of UY Scuti offers both challenge and beauty. It complicates every measurement by absorbing and scattering the very light needed to study the star, yet it also provides a laboratory for understanding how massive stars lose mass and form dust. Through the haze of scutum telescopes capture its faint infrared glow, mapping the interplay between radiation and matter on scales far beyond any human experiment. Within this vast envelope, atoms born in nuclear reactions drift outward to become dust, and that dust in turn becomes part of future worlds. It is a slow exchange measured in millennia, carried out in silence. The dust shell of UY Scuti is not merely a cloud, but a memory, a record of a star in transformation, preserving traces of its life even as it fades into the larger night of the Milky Way. Between the visible surface of UY Scuti and the outer dust shell lies a region in constant motion, where gas flows outward in a slow, unbroken wind. This is the stellar wind zone, a layer that bridges the dense atmosphere and the near vacuum of interstellar space. Here the balance between gravity and radiation tilts slightly outward, allowing the star's luminous pressure to lift matter away from its surface. Each second, countless atoms of hydrogen, helium, and heavier elements drift upward from the photosphere, propelled first by thermal motion and then accelerated by light. This process is gentle but relentless. Over thousands of years, the star has shed an enormous fraction of its original mass through this slow evaporation, building the surrounding envelope that now defines its outermost reach. In this zone, temperature, density and motion vary continuously. Close to the star, the gas remains hot and partly ionized, glowing faintly as atoms collide and recombine. Farther out, as the pressure drops, the gas cools and transitions into molecules that later condense into dust. Astronomers trace these transitions through spectroscopy, identifying signatures of hydrogen, carbon monoxide, and water vapor. Each spectral line reveals not only chemical composition but also velocity as the light is shifted slightly by motion, away from the observer. These shifts confirm that the wind expands steadily at a few tens of kilometers per second, slow by stellar standards, but enormous compared with anything on Earth. The mechanism driving this flow begins deep within the atmosphere. UY Scuti's outer layers are convective with massive cells of gas rising and sinking in cycles. When rising plumes reach the surface, they carry energy that heats the surrounding regions and creates localized shocks. These shocks push material outward, temporarily reducing the hold of gravity. At the same time, the star's intense radiation exerts pressure on atoms and dust grains. Photons striking these particles impart momentum, much like wind pushing a sail. In dense regions where dust forms, this effect becomes significant, providing the main force that drives the outflow. As radiation pushes the dust outward, collisions between dust and gas drag the gas along, coupling the two components into a single expanding wind. This delicate interplay between light, dust, and gas defines the structure of the stellar wind zone. Without dust, radiation pressure alone would not suffice. Without radiation, the dust would not move. The result is a self-regulating process sustained by the star's own energy. Observations across multiple wavelengths reveal that the wind is not uniform. High-resolution interferometry shows variations in brightness and velocity around the star, suggesting that mass loss occurs in localized streams rather than evenly across the surface. Some regions expel gas more vigorously, possibly due to stronger convection or magnetic activity. These irregularities give the wind a patchy texture, with denser clumps embedded in a more diffuse flow. Over time, such inhomogeneity can lead to the formation of arcs or spiral structures in the surrounding dust. The pattern depends on the star's slow rotation, which gently modulates how material escapes. Because UY Scuti rotates much more slowly than the Sun, its vast radius diluting any initial spin, these features evolve, gradually changing shape over centuries. The physical conditions in the stellar wind zone are extreme yet fragile. Temperatures range from several thousand degrees near the base to only a few hundred farther out. Densities fall rapidly, dropping by orders of magnitude within a few stellar radii. In this tenuous environment, collisions between particles become rare, and radiation dominates the transfer of energy. Molecules form briefly before being broken apart again by ultraviolet light. Magnetic fields thread through the gas, though their strength is weak compared to that of compact stars. Even so, these fields can channel flows, creating preferred directions for mass loss. Polarized light measurements reveal hints of alignment in the dust grains, evidence that magnetism influences their orientation as they leave the star. The combined effect of these forces produces a flow that is simultaneously ordered and chaotic, steady in the long term, yet full of fine-scale turbulence. Studying the stellar wind of UY Scuti helps astronomers understand how massive stars evolve toward their end stages. The rate at which material escapes determines how much mass remains in the core, and therefore what kind of explosion will follow. If too much mass is lost, the remnant may collapse quietly into a white dwarf. If enough remains, it can produce a supernova and perhaps leave behind a neutron star. Measuring this rate is challenging because it depends on assumptions about the geometry and composition of the outflow. Infrared and radio observations, which trace emission from molecules like carbon monoxide, provide the most direct clues. These data suggest that UY Scuti's wind removes roughly a 10,000th of a solar mass each year. Although this seems small over the few 100,000 years of its red supergiant phase, the total loss becomes immense, rivaling several times the mass of the Sun. This steady depletion will eventually expose the hotter inner layers and alter the balance of pressure supporting the outer atmosphere. Within the wind zone, light and matter interact continuously. Photons leaving the photosphere are scattered, absorbed and re-emitted countless times, creating a diffuse glow that merges into the infrared background. This region is also where much of the variability observed from Earth originates. As the outer layers pulsate, the density and temperature at the base of the wind change, modulating the rate at which material escapes. When the star expands, the gravitational hold on the atmosphere weakens, enhancing the flow. When it contracts, the flow diminishes. These oscillations lead to subtle fluctuations in the brightness and spectral lines that observers record as periodic variations. Each cycle represents a slow exhalation and inhalation of stellar material on scales that dwarf the orbits of planets. The transition from the photosphere to the wind is not sharp but continuous. There is no boundary where the star ends and space begins, only a gradual thinning of gas until it becomes indistinguishable from the surrounding medium. For this reason, defining the radius of UY Scuti is partly a matter of convention. Astronomers choose a level of optical depth, a measure of how opaque the gas is to mark the nominal surface. But beyond that point, the atmosphere continues for many radii carried outward by the wind. This extended structure means that a large fraction of the star's apparent size arises not from the dense interior, but from the translucent layers of gas and dust hovering above it. The stellar wind zone thus contributes directly to the impression of vastness that defines UY Scuti. Even at great distance, the influence of this wind extends outward into the galactic environment. The expelled material adds momentum and energy to the surrounding medium, stirring nearby gas clouds. When the wind encounters regions of higher density, it can create bow shocks, curved fronts of compressed gas that trace the star's motion through space. These features, faint but detectable in infrared images, mark the interface between the stellar and interstellar domains. Over time, as the star loses more mass, the wind may become stronger and faster, sweeping a larger volume. Eventually, the cumulative effect of many such stars contributes to the structure of the Milky Way's spiral arms, enriching them with heavy elements and sculpting their form. In the case of UY Scuti, the stellar wind zone embodies transition. It is the place where a star's internal energy becomes motion, where radiation turns matter into flow, and where the boundaries between the star and the galaxy blur. Through this unceasing wind, the supergiant both diminishes and endures, shedding parts of itself, even as its light continues to shine. The particles now drifting outward will travel for millions of years before merging with other clouds long after the star itself has ended. The zone that surrounds UY Scuti, though invisible to ordinary sight, is the stage upon which the quiet drama of stellar transformation unfolds, a movement of heat and gravity, pressure and dust carried out in silence across immeasurable space. Beyond the zone of steady wind lies a region where the air of the star becomes increasingly rarefied, yet still bound by gravity. This is UY Scuti's extended atmosphere, a transitional domain between the visible surface and the surrounding interstellar medium. In this vast expanse, the familiar idea of a stellar surface loses meaning. The atmosphere thins, gradually stretching outward over distances many times the Sun's diameter. Within it, temperature and density decline together, creating layers of gas that glow faintly and scatter the light from below. To instruments on Earth, this region appears as a subtle halo that shifts in brightness as the star pulsates. It is here that the star's colour deepens, It's light, filtered through cool molecular layers that absorb and re-emit radiation in complex ways. The extended atmosphere is not a fixed structure, but a living, breathing field of motion. Enormous convection cells from beneath the photosphere push gas outward while gravity pulls it back. In this perpetual balance, waves of expansion rise and fall across the star's outer layers. Each wave carries heat and momentum, setting the atmosphere into oscillation. Because the gas is thin, these waves travel long distances before dissipating, creating regions that shimmer with fluctuating density. From a distance, the result is a surface that appears to flicker and shift subtly over time, its brightness modulated by slow currents of plasma. Chemically, the extended atmosphere of UY Scuti is rich and diverse. Temperatures range from about 3,000 degrees Celsius near the photosphere to only a few hundred farther out. Within that gradient, molecules form and break apart continuously. Oxygen combines with hydrogen to create water vapor with titanium to form titanium oxide, and with silicon to produce silicate dust precursors. Carbon monoxide, stable and abundant, acts as a regulator, binding whichever element, carbon or oxygen, is in excess and determining the remaining chemistry. These compounds absorb light at specific wavelengths, producing the deep molecular bands that dominate the spectra of red supergiants. To astronomers, these features serve as fingerprints revealing both composition and temperature. Each line of absorption corresponds to a layer within the atmosphere, and by analysing how those lines change over time, scientists infer how the star's outer regions expand, cool and contract in rhythm with its variability. The atmosphere also reveals the dynamics of mass loss. As the gas rises and cools, radiation pressure and pulsation begin to overcome gravity. Material lifted high enough becomes part of the slow outward flow feeding the wind. In some phases of the pulsation cycle, this process strengthens, producing bursts of increased mass loss. In others, it weakens, allowing the atmosphere to settle temporarily. The balance between these two states gives UY Scuti its semi-regular variability. Observers have recorded changes in brightness with periods of a few hundred days each cycle, reflecting the gentle breathing of the star's extended layers. The amplitude of these variations is modest, only a fraction of a magnitude, but over time they shape the formation and density of the circumstellar environment. Light from UY Scuti passing through its extended atmosphere acquires a character that is neither purely emission nor absorption, but a blend of both. The gas is partially transparent, so some photons escape directly, while others scatter or are re-emitted after absorption. This scattering creates a diffuse glow around the star, visible in high-resolution interferometric images. The atmosphere's opacity depends strongly on wavelength, meaning that the star's apparent size changes when observed in different colors of light. In the infrared, where the gas is more transparent, the star appears smaller. In visible wavelengths, where molecular absorption is stronger, it appears larger. This wavelength-dependent radius is a defining feature of red supergiants and explains why their measured dimensions vary between instruments. In UY Scuti's case, such differences amount to hundreds of millions of kilometers, an uncertainty that illustrates the fluid nature of the star's boundary. The structure of this vast atmosphere is maintained by convection. Within the upper envelope, energy no longer travels efficiently by radiation alone. Instead, hot gas rises, cools as it expands, and then sinks back downward, carrying heat in great circulating loops. On the Sun, similar convection forms granules the size of continents. On UY Scuti, the equivalent cells may span distances greater than the orbit of Earth. Each cell evolves over months or years, reshaping the surface brightness pattern of the star. Astronomers using interferometers have detected these variations as uneven patches of light, confirming that the apparent disk of the star is not uniform but mottled. Such findings reveal the scale of motion within the extended atmosphere, the slow overturn of entire planetary volumes of gas. Within this domain, sound and gravity waves propagate freely. These waves arise from turbulent motion near the photosphere and travel outward through the rarefied gas carrying energy into space. They contribute to heating the outer layers, maintaining temperatures higher than would be expected from simple radiative cooling. This process, sometimes called acoustic or shock heating, links the star's pulsation with its atmospheric stability. Without it, the upper atmosphere would cool too quickly and collapse inward. With it, the region remains inflated and luminous. Magnetic fields may also play a subtle role guiding charged particles along invisible lines of force. Though weak, these fields can influence the formation of small-scale structures and the alignment of dust grains that later condense farther out. The extended atmosphere also serves as a laboratory for understanding the chemistry of evolved stars. Within it, atoms forged in nuclear fusion interact under low-pressure conditions similar to those found in the early stages of planetary nebulae. Observing this environment allows scientists to trace how elements move from stellar interiors into the interstellar medium. Every molecule detected around UY Scuti represents matter that was once part of its deeper layers, now freed to participate in the galaxy's wider cycles. The oxygen-bearing compounds that dominate its atmosphere will ultimately contribute to the silicate dust that fills space between stars. In this way, the extended atmosphere is both a product and a precursor formed by the star's energy, and destined to enrich future generations of cosmic matter. From a physical perspective, the extended atmosphere blurs the distinction between the star and its surroundings. Gravity still binds the gas loosely, but radiation and motion constantly erode that hold. Over time, the atmosphere's outer limit drifts outward, feeding the stellar wind. The transition between bound and unbound matter is gradual, taking place across several stellar radii. Within this transitional layer, the escape velocity and the local sound speed become comparable, allowing gas to flow away almost effortlessly. This is the region where the star's identity begins to merge with space itself. Seen through the instruments of modern astronomy, UY Scuti's extended atmosphere is not a static shell, but an ocean of glowing gas folding and refolding upon itself. In images captured by interferometers, its disk wavers gently brightness, fluctuating as cells rise and fall. The colour deepens toward crimson at the edges, where cooler molecules dominate, and brightens toward orange near the centre, where the view penetrates deeper layers. Around the whole sphere stretches a faint glow, the visible signature of the extended atmosphere blending into the wind beyond. The impression is one of vast calm, a structure, immense yet delicate, dynamic yet unhurried. Within this expanse, energy generated deep in the core is transformed into motion chemistry and light, eventually to drift outward across the galaxy. For all its complexity, the extended atmosphere of UY Scuti remains governed by the same principles that shape every star: gravity's inward pull, balanced by pressure's outward push, modified here by the subtle effects of radiation convection and molecular cooling. The result is a system on the edge of equilibrium, sustained by forces that change slowly but never cease. Each atom within this envelope is part of a grand circulation, rising, cooling and falling again before its final release into space. In that endless movement lies the quiet persistence of a giant nearing the close of its long existence, a vast atmosphere still breathing softly beneath the shield of scutum. At the visible surface of UY Scuti lies a boundary known as the photosphere, the layer from which most of the star's light escapes into space. Unlike a solid surface, It is a depth within the gaseous envelope where the plasma becomes opaque to visible radiation, marking the transition from the internal layers that trap light to the outer layers that release it. To an observer, the photosphere defines the star's apparent disk, the glowing sphere that telescopes and detectors record. For a red supergiant, this region is immense and diffuse, extending across distances so vast that light takes minutes to cross. The temperature here averages around 3000 degrees Celsius cool by stellar standards, giving the star its deep orange-red colour. Every photon that leaves the photosphere carries information about the physical conditions at that moment: temperature, density, velocity, and composition. Over time, these conditions shift subtly as the star pulsates, causing its brightness to vary in cycles lasting many months. The changes are gentle but measurable, revealing that even at the visible surface, the star is alive with slow movement. The photosphere is shaped by convection. Beneath it, energy generated in the core rises through layers of gas by the motion of enormous convective cells. When these cells reach the surface, they release heat and light, creating bright regions where hot material wells upward. Surrounding these are darker areas where cooler gas sinks back toward the interior. On the Sun, such convection produces granules about the size of continents lasting minutes before dissolving. On UY Scuti, the scale is almost beyond comprehension. Each cell may span distances greater than the orbit of Earth and persist for months or even years. The combined effect of a few dozen of these immense cells gives the photosphere a mottled appearance, with brightness varying across its face. Interferometric observations have detected such asymmetries, confirming that the surface of a red supergiant is not uniform but patterned by slow rolling waves of plasma. These patterns shift gradually as cells evolve, merging and dividing, reshaping the visible disk in a rhythm that mirrors the deeper convective flow. At this level, the gas is dense enough for light to interact strongly with atoms and molecules. The spectrum of UY Scuti's photosphere is dominated by absorption lines from titanium oxide, vanadium oxide, and other molecules stable at its relatively low temperature. These features give the light a rich, complex structure, allowing astronomers to determine temperature and surface gravity with precision. The presence of such molecular bands distinguishes red supergiants from hotter stars, whose spectra are defined by atomic transitions instead. Because the photosphere's conditions fluctuate during each pulsation cycle, these spectral lines shift slightly in wavelength, a Doppler effect revealing the slow breathing motion of the surface, expanding, cooling, and then contracting and warming again. This motion, though invisible in real time, alters the star's brightness by a few tenths of a magnitude, enough to produce the variability recorded by observers for decades. The brightness variations also depend on opacity, which changes with temperature. When the star expands, the gas cools and becomes more transparent, allowing radiation to escape more easily and temporarily brightening the star. As the atmosphere contracts, it heats up, increasing opacity and dimming the light. These oscillations form a feedback loop that maintains the semi-regular variability characteristic of UY Scuti. Although the amplitude of these changes is small compared with that of mirror-type variables, the underlying mechanism is similar pulsation, driven by partial ionization zones within the outer envelope. In these zones, hydrogen and helium alternate between neutral and ionized states, absorbing and releasing energy that powers the rhythmic expansion and contraction of the photosphere. Because the photosphere emits most of the visible and near-infrared light, it is also the region most directly observed. Interferometers operating in the near-infrared have resolved the disk of UY Scuti into measurable dimensions, revealing its angular size and confirming that the apparent radius depends on wavelength. The results show that the star's edge is not sharp but blurred by the gradual decline in density with height. The limb darkening seen in smaller stars becomes extreme here. The center of the disk appears brighter than the edges because we see deeper into the hotter layers when looking straight on. Toward the rim, our line of sight passes through cooler gas, reducing brightness and giving the star a soft rounded profile. These observations contribute to refining models of radiative transfer in extended atmospheres, which are essential for understanding how such stars lose energy and mass. Magnetic fields, though weak, may influence the behavior of the photosphere. Observations of polarization in the emitted light suggest the presence of magnetic activity, perhaps generated by the slow rotation and turbulent convection beneath the surface. Such fields could guide localized flows of plasma forming spots or arcs, where material is ejected preferentially. These regions would correspond to slightly brighter or darker patches on the surface, consistent with the irregularities seen in high-resolution imaging. The interaction between magnetism and convection adds complexity to the star's variability, producing patterns that evolve over years rather than months. In this way, the photosphere records both short-term pulsation and long-term structural change, offering a dynamic portrait of the star's outer behavior. From a physical standpoint, the photosphere represents the last barrier to direct observation of stellar interiors. Light generated in the core takes thousands of years to diffuse outward, scattering endlessly through dense plasma before emerging from this thin layer. Once free, it travels across the galaxy almost unchanged until it reaches our telescopes. Each photon is thus a messenger from the surface of a single star, carrying with it the memory of temperature, motion, and composition at the instant it escaped. In the case of UY Scuti, those photons must still traverse thick interstellar dust before they arrive, but the information they contain remains largely intact. By decoding their wavelengths, astronomers reconstruct conditions within a star so distant that its light began its journey before recorded human history. The photosphere also defines the connection between the star and its wind. Gas that reaches this level is no longer in hydrostatic equilibrium. Small perturbations from pulsation or convection can push it beyond the point where gravity dominates. From there, the material drifts outward, cools, and joins the expanding envelope. This link between surface dynamics and mass loss is crucial to understanding the life cycle of red supergiants. Tiny fluctuations in pressure or temperature can determine whether matter escapes or falls back. In the case of UY Scuti, the balance leans toward escape, sustaining the steady flow that feeds its circumstellar shell. The photosphere is therefore both boundary and gateway, the layer through which the star slowly transfers its substance into space. To visualize the scale of this region is to approach the limits of comprehension. A single convection cell on the photosphere may be larger than the distance from the Sun to Earth, and the layer's thickness itself extends over millions of kilometers. Yet from Earth, the entire star appears as a faint point of light, its immensity compressed by distance into a single speck in the constellation Scutum. Through spectroscopy and imaging, astronomers translate that point into structure, color, and motion, reconstructing a world of seething plasma far beyond sight. Within that sphere of light, temperature gradients, molecular chemistry, and convection combine to create the observable face of one of the galaxy's largest stars. In the slow rhythm of UY Scuti's variability, the photosphere embodies the balance between stability and change. It releases light steadily enough to maintain the star's immense luminosity, yet it trembles with internal motion that hints at the instability to come. As the star continues to lose mass and evolve, this layer will shift outward and cool, further eventually merging with the atmosphere and wind beyond. For now, it remains the luminous skin of a vast aging sun, its colour deep, its light filtered through molecular haze, its surface an ever-changing landscape of heat and motion, suspended in the darkness of Scutum. Deep within UY Scuti, far below the visible surface, lies the source of all its light and motion. The energy that sustains this immense red supergiant originates in nuclear reactions, occurring within its core where temperature and pressure are high enough to fuse atomic nuclei. From that inner furnace, energy must travel outward through millions of kilometers of dense gas before escaping from the photosphere. The way this energy moves determines the star's structure and appearance. Inside, UY Scuti radiation and convection share the task of transport, but in its outer regions, convection dominates. Radiation alone cannot carry the vast energy flux because the gas is opaque. Photons are absorbed and re-emitted countless times, trapped within a maze of ions and atoms. Instead, energy rises through bulk motion, great currents of plasma carrying heat from deep layers to the surface. The visible surface, where these currents finally release their energy as light, is the outer expression of this slow internal migration. In the deepest layers, where density and temperature reach extreme values, radiation remains the main conveyor. Here, photons diffuse outward through the dense plasma, scattering off electrons and ions in a random walk that may take hundreds of thousands of years. Gradually, as temperature decreases and the gas becomes less ionized, convection begins to take over. The transition from radiative to convective transport marks the beginning of the extended envelope that defines red supergiants. In this region, the material becomes unstable to rising and sinking motions. Hotter, lighter gas moves upward, while cooler, denser gas sinks, forming vast convective cells. The scale of these cells in UY Scuti is enormous, each one spanning distances that would encompass the entire orbit of Earth. Within them, material rises at speeds of several kilometers per second, slows as it cools, and then descends again in long arcs. This continuous overturn keeps the energy flowing and also mixes the star's chemical elements, bringing processed material from deeper zones toward the surface. The efficiency of convection in UY Scuti explains its relatively cool surface. The movement of gas carries energy outward so effectively that temperature gradients become shallow. Radiation is no longer trapped, and pressure support comes from the turbulent motions themselves. The star's outer layers thus expand, producing the immense radius that characterizes red supergiants. The trade-off is density. As the outer layers stretch, they thin dramatically, so that the average density of UY Scuti's envelope is far lower than that of air. In this tenuous environment, convection operates on scales of millions of kilometers, forming sluggish but powerful currents. The pattern resembles a slow, boiling ocean of plasma. Each rising plume carries material from the interior, enriched with helium and other fusion products, and each sinking plume returns cooler gas downward, maintaining a steady circulation that persists for centuries. Energy transport in this regime also generates the irregular brightness variations observed from Earth. Because the convection cells are few and immense, the surface never displays uniform luminosity. As some regions brighten and others dim, the integrated light fluctuates subtly, giving rise to the star's semi-regular variability. Over timescales of hundreds of days, these patterns shift as individual cells evolve or merge. This behavior differs from that of smaller, more stable stars where millions of small granules average out any irregularities. On UY Scuti, the convection pattern is coarse and dynamic, imprinting its slow rhythm on the emitted light. The resulting variations combine with the longer pulsation cycles to create a complex pattern of change that observers record as alternating intervals of brightening and fading. Convection also influences the star's internal chemistry. In smaller stars, layers of different composition remain distinct, but in red supergiants, the deep convective envelope dredges material from the interior to the surface. This process brings elements such as carbon, nitrogen, and oxygen produced in nuclear fusion into the observable atmosphere. Spectroscopic studies of UY Scuti reveal these signatures, confirming that its surface is enriched in products of the CNO cycle. The upward transport of such material not only alters the star's spectrum, but also affects its future evolution. As heavy elements accumulate in the outer layers, the opacity changes, modifying how radiation interacts with the gas. This feedback can either stabilize or destabilize the star's structure, influencing its lifespan as a red supergiant. The convective motions within UY Scuti are accompanied by turbulence vortices and waves that propagate through the envelope. These motions convert some of the thermal energy into mechanical energy, producing sound and gravity waves that travel outward. As they move into the thinner layers near the surface, they can steepen into shocks, heating the atmosphere and contributing to mass loss. The same process that transports energy thus also drives the gradual shedding of material. Modern three-dimensional simulations of red supergiants attempt to reproduce this complex interplay of convection, radiation, and pulsation. The models show that large-scale convective cells can persist for long periods, interacting with pulsations to produce asymmetric outflows. Observations of UY Scuti's brightness distribution align well with these theoretical predictions, reinforcing the view that convection is the dominant mode of energy transport in such stars. The role of radiation, though diminished in the outer envelope, remains vital in deeper layers. Here, photons carry the energy generated by fusion toward the regions where convection can take over. The competition between radiative and convective processes determines the boundary between the core and the envelope. This balance shifts as the star evolves, with convection penetrating deeper as the core contracts and the outer layers expand. The result is a structure in constant adjustment. Energy flows outward, while the zones through which it travels slowly change position. The dynamic equilibrium maintained between energy production and transport defines the star's current state. Magnetic fields may arise from the motion of ionized gas within these convective layers. Although weak compared with those of smaller, denser stars, they can still influence the flow of energy by redirecting plasma and modifying the efficiency of mixing. Magnetic activity might also produce localized heating or cooling, generating subtle patterns on the photosphere. Detecting such fields directly in a star as distant as UY Scuti is difficult, but evidence from similar red supergiants suggests they exist, generated by dynamo action within the turbulent interior. These fields could help channel the outflow of mass and contribute to the asymmetry observed in the surrounding dust. The transport of energy from the core to the surface is ultimately a balancing act between pressure and gravity, heat and radiation. If energy production exceeds the ability of the envelope to carry it away, the star expands until equilibrium is restored. If the flow becomes too efficient, the star contracts. UY Scuti's current size reflects the outcome of millions of years of such adjustments. Its enormous radius ensures that the energy generated deep inside can escape at a temperature low enough to maintain stability. Yet this stability is temporary. As fusion proceeds to heavier elements, the core contracts and the outer layers respond by expanding further, altering the balance once more. The gentle light we see today represents only a transient state in a slow sequence of readjustments. The physics of energy transport within UY Scuti illustrates the unity of stellar processes. From the smallest atoms fusing in the core to the largest convective plumes rising toward the photosphere, every layer is connected through the continuous flow of energy. The photons that leave the surface tonight began their journey as nuclear reactions millions of years ago, their path delayed by countless scatterings within the dense interior. Their emergence marks the end of a journey across a world of plasma turbulence and gravity. The visible calm of UY Scuti's red light conceals a dynamic interior, a vast engine converting mass into energy and distributing it outward through the interplay of radiation and convection. In this quiet, continuous movement, the star maintains its balance, radiating steadily into the darkness of scutum while its internal fires burn on. Beneath the convective envelope of UY Scuti lies the core, the true heart of the star, and the origin of the energy that sustains its glow. Here, temperatures reach hundreds of millions of degrees Celsius, and densities become so great that atomic nuclei collide often enough to overcome their natural repulsion. Fusion, nature's most efficient energy source, takes place in concentric shells, arranged by the sequence of nuclear reactions that have unfolded over the star's lifetime. Each layer represents a different stage in this process, stacked like invisible spheres within the star's interior. The innermost zone, now depleted of hydrogen, fuses helium into carbon and oxygen. Surrounding it are shells where hydrogen continues to fuse in thin bands powered by heat leaking outward from below. Beyond these lie progressively cooler regions where heavier elements form as the star evolves. Together they create a structure that mirrors the logic of nuclear physics. Each successive reaction requires higher temperature and produces less energy, forcing the star to burn through its reserves in ever shorter phases. When UY Scuti first formed, it was dominated by hydrogen fusion in the core, combining 4 protons into one helium nucleus through the CNO cycle, a process efficient only at high temperatures sustained by massive stars. Over millions of years, hydrogen in the central region was exhausted, leaving a core rich in helium. With fusion no longer providing pressure support there, gravity caused the core to contract and heat up, igniting helium burning in its center, while hydrogen fusion shifted to a shell around it. This transition marked the beginning of the red supergiant phase. The outer layers expanded, cooled and reddened, while the inner regions became a complex arrangement of nested fusion zones. In UY Scuti's present state, helium fusion likely proceeds through the triple alpha process, in which 3 helium nuclei combine to form carbon, releasing gamma radiation and maintaining equilibrium. As the core contracts further, helium will eventually be exhausted, and fusion of heavier elements will ignite in new shells, producing oxygen, neon magnesium and silicon. Each new reaction occurs faster than the one before, compressing the remaining lifespan of the star into shorter and shorter intervals. The structure of these fusion layers is invisible to direct observation, but can be inferred from models of stellar evolution and from the spectral signatures of material dredged up by convection. The relative abundances of carbon, nitrogen and oxygen in UY Scuti's atmosphere reveal the byproducts of the CNO cycle and confirm that helium fusion has been active for some time. Deep inside, conditions are extreme temperatures of hundreds of millions of degrees and pressures billions of times greater than Earth's atmosphere. Under such conditions, matter behaves as plasma, a mixture of nuclei and electrons moving freely in dense fluid. Radiation is trapped by the opacity of this plasma, and convection transports much of the energy outward. The boundary between core and envelope is not sharply defined, but marked by gradual changes in composition and density, where burning shells alternate with inert zones of ash from previous reactions. Each burning layer contributes differently to the overall luminosity. The hydrogen shell produces a steady output that supports the extended envelope, while the helium core provides the bulk of the energy sustaining the star's expansion. As fusion proceeds, the core contracts further and grows hotter, igniting new reactions in succession. The sequence is predictable, but dramatic carbon burning produces oxygen, and neon burning yields magnesium and silicon burning culminates in iron. Once iron accumulates in the center, no further energy can be extracted through fusion, for fusing iron consumes rather than releases energy. At that point, the balance between pressure and gravity collapses, leading to the catastrophic implosion that will one day mark the end of UY Scuti's life. This final stage, though still distant, is already foreshadowed by the structure now forming deep within. The layered arrangement of fusion zones resembles the rings of a tree or the layers of an onion, but in motion, not static. Each shell burns at a different rate, expanding or contracting as the conditions change. Shock waves and sound waves propagate between them, coupling the activity of the core with the surface. This connection explains why variability seen at the photosphere reflects processes occurring far deeper inside. The pulsations of UY Scuti's outer layers are ultimately driven by changes in energy production within these fusion shells. When output increases slightly, the outer envelope expands and cools. When it decreases, the envelope contracts and heats. Thus, the star's visible rhythm originates from nuclear events occurring millions of kilometers below. The physics governing fusion within UY Scuti follow the same laws that power all stars, but the scale amplifies every effect. Small fluctuations in temperature can lead to enormous changes in reaction rates, because fusion depends sensitively on heat. A 1% rise in temperature within the helium-burning core can double the energy output, forcing the surrounding layers to adjust. These rapid responses create a feedback loop. The core expands, cooling itself, and then contracts again, reheating, establishing a cycle of subtle oscillation. This thermal instability contributes to the irregular luminosity of red supergiants. Observing these fluctuations from afar allows astronomers to infer the internal energy generation, indirectly turning small variations in brightness into evidence of nuclear change. The energy produced in the core travels outward primarily by radiation, diffusing slowly through layers of plasma. Photons generated by fusion scatter countless times before reaching the convective envelope, where energy transport switches to large-scale motion. The journey from the core to the surface may take hundreds of thousands of years, even though light moves at incredible speed, because each scattering delays its progress. This slow diffusion smooths fluctuations in energy generation, ensuring that the star's outward brightness remains relatively stable despite the turbulence within. The photons that finally reach the photosphere tonight began their journey when the star was younger, carrying with them the ancient memory of nuclear reactions long past. Within these inner layers, the composition of matter changes continuously. As helium converts to carbon and oxygen, neutrinos, nearly massless particles, escape freely, carrying away a fraction of the energy. Though they play little role in the star's structure, now their eventual surge during core collapse will mark the end. For the moment, however, they drift silently through the outer layers, undetectable, except to instruments designed to capture their rare interactions. Their presence reminds astronomers that deep inside, UY Scuti nuclear reactions are ongoing at unimaginable intensity, invisible but essential to the star's continued existence. The fusion layers beneath the surface also define how UY Scuti will die. Stars of lower mass end their lives quietly shedding their outer envelopes to reveal white dwarfs. But for a star of UY Scuti's magnitude, the core's eventual composition of iron ensures a far more violent outcome. Once the fusion chain halts, the outward pressure supporting the envelope will vanish. Gravity will drive the core to collapse in a fraction of a second, compressing matter to nuclear density and igniting a shock wave that tears through the surrounding layers. The explosion that follows a supernova will briefly outshine an entire galaxy, dispersing heavy elements into space and leaving behind either a neutron star or a black hole. The dust shell now drifting around UY Scuti will then be swept outward by that final blast, enriching the scutum arm with the remnants of its life's work. For now, the core continues its ordered, burning, stable, yet restless, feeding the star's enormous luminosity. The fusion layers beneath UY Scuti are unseen, but they are the engine of its existence, the hidden structure that maintains its brilliance and defines its fate. From this depth comes the steady energy that warms the vast photosphere, drives the wind, and illuminates the dust. The light we see across the galaxy begins here in a dense, silent crucible, where matter transforms into energy, sustaining for a brief cosmic moment the radiance of one of the Milky Way's grandest stars. Within UY Scuti, every movement of light and matter is ruled by gravity. It is the inward force that holds the star together, balancing the outward pressure produced by nuclear fusion and the turbulent motion of gas. In the earlier stage of its life, this balance was perfect, a steady equilibrium between collapse and expansion. But in its current form as a red supergiant, that balance is fragile. The star's mass, estimated to be between 20 and 30 times that of the Sun, presses inward with enormous strength, yet the outer layers are so diffuse that gravity's grip there is weak. In those regions, the force that binds the star together barely exceeds the gentle push of radiation and the momentum of the stellar wind. Each atom of gas on the surface hovers near escape, balanced delicately between falling back and drifting into space. It is this tension that defines UY Scuti's structure and its destiny. The gravitational field of such a star is strongest at the core, where density peaks at millions of times that of water. Their gravity compresses matter into states that cannot exist under any earthly condition, forcing electrons and nuclei into close proximity and maintaining the high pressure necessary for fusion. Yet as one moves outward from the center, the strength of gravity diminishes rapidly. By the time it reaches the outer atmosphere, the pull becomes faint, and a small perturbation, a burst of convection, a pulse of radiation pressure can lift material free. This gradient in gravitational strength creates the layered character of the star, a dense hot core surrounded by vast, nearly weightless shells that extend into the stellar wind. The visible surface, though immense, represents only a tiny fraction of the total mass. Most of the matter lies concentrated toward the center, where gravity dominates all other forces. The coexistence of immense mass and low density produces paradoxical effects. The surface gravity of UY Scuti, though derived from enormous total mass, is much weaker than that on the Sun because of the star's vast radius. A particle released from its outer atmosphere would fall slowly, taking hours to descend through the thin gas. This gentleness allows the star to lose mass continuously, its outer layers flowing away in a persistent wind. Each year, radiation pressure overcomes gravity for a small portion of the gas, lifting it outward, where it cools and condenses into dust. The resulting mass loss rate, although minuscule by human standards, accumulates over cosmic time to reshape the star. The loss of even a small fraction of its mass can alter the internal balance of forces, changing how the core contracts and how fusion proceeds. To understand this balance, astronomers rely on the principle of hydrostatic equilibrium, which states that at every depth inside a star the inward pull of gravity is exactly matched by the outward pressure of gas and radiation. If the two forces become unequal, the star adjusts. Expansion reduces pressure, contraction increases it. In UY Scuti, this equilibrium persists globally, yet locally it wavers. Convection disrupts the uniformity, creating regions where pressure and gravity compete dynamically. When a convective plume rises, it temporarily reduces density in its path, allowing gravity to draw surrounding material inward. The resulting turbulence maintains the star's outer layers in constant motion. On average, the balance holds, but the path to that balance is one of continual adjustment. This perpetual readjustment gives the star its irregular surface and its variability in brightness. Gravity also governs the relationship between the core and the envelope. As fusion in the core converts lighter elements into heavier ones, the total number of particles available to provide pressure decreases, causing the core to contract. The contraction releases gravitational energy, heating the surrounding layers and driving expansion in the envelope. Thus, even as the interior shrinks, the outer regions swell. This seesaw between core collapse and envelope expansion defines the late evolution of massive stars. For UY Scuti, the process has produced a radius hundreds of times greater than that of the Sun, a structure so extended that gravity's influence at the surface verges on vanishing. The star now teeters near the Eddington limit, the point at which radiation pressure and gravity are in near equilibrium. Should luminosity increase slightly, radiation would overpower gravity, ejecting material more rapidly and accelerating mass loss. The interplay between gravity and mass loss shapes the star's path toward its end. Each atom lost to the wind carries momentum outward and reduces the total mass binding the remaining material. As gravity weakens, the star becomes less able to confine its envelope, allowing the wind to strengthen further. This feedback loop ensures that red supergiants like UY Scuti gradually peel away their outer layers before death. The stripped mass enriches the surrounding space with heavy elements, while the core grows denser and hotter. Eventually, when fusion can no longer produce enough energy to counter gravity, the balance will fail completely. In a brief catastrophic moment, gravity will win. The core will collapse in upon itself at nearly the speed of light, crushing matter into neutron-degenerate form. The shock generated by this collapse will rebound through the envelope, producing a supernova explosion that unbinds what remains of the star. Until that final instant, gravity continues its quiet rule. It is present in every fluctuation, every pulse of light, every slow drift of dust away from the surface. Even the variability of UY Scuti's brightness owes part of its rhythm to the competing influences of gravitational compression and expansion. As the outer layers cool and sink, they increase density, strengthening gravity's pull and drawing the material inward. The compression raises temperature, increasing radiation pressure, which then pushes the layers back outward. This oscillation repeats endlessly, keeping the star in dynamic equilibrium. To observers, it manifests as a slow alternation of brightness that spans months, the visible sign of a balance continually tested but never broken. Measurements of UY Scuti's mass are indirect, inferred from models of stellar evolution and from its luminosity. The relation between mass and brightness for massive stars suggests an initial mass of perhaps 25 times that of the Sun, now reduced through steady loss. Despite its size, its mass places it below the extreme hypergiant class where instability dominates. This intermediate position makes it especially valuable to study massive enough to exhibit strong winds and deep convection, but stable enough to persist in relative equilibrium. The gravitational binding energy of the star, an immense reservoir, remains the ultimate source of its structural integrity. Without it, the expanding envelope would have dispersed long ago. Gravitational potential also shapes the geometry of the surrounding dust shell. As expelled material moves away, it slows under the star's pull, forming dense regions before drifting free. The transition from bound to unbound gas occurs at the escape velocity, only a few tens of kilometers per second for such a diffuse star. This slow escape gives the wind its smooth profile and ensures that mass loss remains steady rather than explosive. The gentle nature of this flow contrasts sharply with the violent end that gravity will later impose when equilibrium finally collapses. The same force that now restrains the envelope will one day trigger its destruction. To visualize gravity's influence within UY Scuti is to picture a scale spanning extremes. At the center, unimaginable compression; at the surface, near weightlessness. Between these poles stretches a gradient of forces maintaining a precarious balance. The star's vast appearance belies the power operating unseen within a gravitational pressure capable of countering radiation from billions of suns. Every photon escaping into the Milky Way has fought its way through this field, climbing out of a gravitational well so deep that its wavelength lengthens slightly a minute redshift that records the star's immense pull. Gravity leaves its signature not only in motion, but in light itself. For UY Scuti, mass and gravity are the invisible architecture of its existence, the silent framework upon which its luminosity, temperature and shape depend. Without the inward weight of its own matter, the star would disperse. Without the outward fire of fusion, it would collapse. The tension between these forces sustains it for the brief remainder of its life, holding it steady in the fragile state astronomers observe today. Eventually, gravity will reclaim what radiation has resisted, compressing the core into a remnant no larger than a city yet containing more mass than the Sun. Until that moment, UY Scuti continues to live in balance, its great weight pressing inward, while light pushes outward, a perfect equilibrium that endures for only a short time in the long history of the galaxy. The light of UY Scuti does not remain constant. Across months and years, its brightness rises and falls in a slow, rhythmic pattern that marks it as a semi-regular variable. These fluctuations are not random, but emerge from deep within the star, the visible expression of pulsations that cause the outer layers to expand and contract. The process is governed by the same delicate balance between gravity and pressure that shapes the entire structure. As energy production in the fusion layers varies slightly, or as internal convection redistributes heat unevenly, the equilibrium shifts. When pressure in the outer zones increases, the star swells, its surface cools and brightness changes. When gravity regains the upper hand, the envelope contracts, reheating and glowing more strongly. This cycle repeats slowly, creating alternating periods of luminosity that observers record as changes in apparent magnitude. For UY Scuti, the full period of one such oscillation spans several hundred days, a steady breathing pattern in which a sphere larger than the orbit of Mars expands and contracts as smoothly as a heartbeat. The mechanism driving these pulsations is known as the Kappa effect, arising from zones in the star's atmosphere where partial ionization occurs. When the gas in such a layer is compressed, it becomes more opaque, trapping heat and raising pressure. The buildup pushes the layer outward, where it cools, recombines, and becomes more transparent. Radiation then escapes, pressure drops, and gravity pulls the layer back inward. The result is a self-sustaining oscillation repeating over long intervals. In UY Scuti, the relevant zones involve hydrogen and helium, which cycle between ionized and neutral states as the temperature fluctuates. Each expansion and contraction produces a corresponding change in the star's radius by as much as 10 to 20%. These variations, though small compared with the star's total size, are enough to modulate its light output, altering its colour and spectral features as well. During expansion, the outer layers cool and emit more light at red and infrared wavelengths. Molecules such as titanium oxide form more readily deepening absorption bands in the spectrum and giving the star a slightly darker hue. When the star contracts, the higher temperature weakens these molecular features and shifts the emission toward shorter wavelengths, making it appear brighter and marginally bluer. These cyclical changes reveal themselves in long-term photometric records as alternating peaks and troughs. The amplitude of variability in UY Scuti is moderate, less dramatic than in mirror-type stars, but more pronounced than in stable supergiants. This behavior classifies it among semi-regular variables, a group characterized by coherent but sometimes overlapping pulsation periods. The result is a light curve that shows a dominant rhythm overlaid with secondary beats, an intricate cadence reflecting the interaction of multiple pulsation modes within the vast envelope. Convection adds another layer of complexity. The enormous cells that dominate energy transport in the outer layers rise and sink on timescales comparable to the pulsation period. Their motion disrupts the regular rhythm, introducing irregularities in timing and amplitude. Some cycles appear stronger, others weaker, depending on how convective flow aligns with the global oscillation. Numerical simulations suggest that only a few dozen such cells cover the surface at any given time, each influencing local brightness. As they evolve and shift, they modify the overall light output, creating small departures from perfect periodicity. To the human eye, these variations might appear as subtle flickers superimposed upon the slower pulse, though the actual timescales extend beyond a lifetime. The pulsations are not confined to the surface but extend deep into the star's interior. As the envelope expands and contracts, pressure waves travel inward, compressing and rarefying the gas throughout the convective zone. These waves interact with the fusion shells, occasionally modulating the rate of nuclear burning. The feedback can either stabilize or amplify the pulsation, depending on the phase relationship between core and envelope. When the two are in sync, energy transfer becomes more efficient, and the amplitude increases. When they oppose, the oscillations dampen. This coupling between layers makes red supergiant variability a complex interplay of thermal, mechanical, and radiative processes. Modern models treat the star as a system of linked oscillators, each zone contributing to the overall rhythm. Spectroscopic observations track the motion of the atmosphere during these cycles. Absorption lines in the spectrum shift alternately toward red and blue, showing the surface moving away from and then toward the observer. The velocity of this motion reaches several kilometers per second, slow in absolute terms but vast when applied to an object of such size. From these shifts, astronomers map the pulsation amplitude and reconstruct the dynamic structure of the outer envelope. They find that different layers move at different times, indicating that the oscillation is not perfectly synchronized. The deep atmosphere lags behind the surface, a consequence of the star's enormous inertia. It takes months for a disturbance to travel from one region to another, and by the time it does, the surface has already changed direction. The entire envelope thus behaves like a slow-motion wave, each layer responding in turn to the pulse initiated below. The consequences of these pulsations extend beyond light variation. Each expansion slightly reduces gravity's grip on the outer layers, enhancing the flow of material into the stellar wind. Each contraction strengthens gravity, slowing the outflow. Over many cycles, this alternating pattern modulates the density of the circumstellar dust shell, creating faint concentric structures visible in infrared images. The dust shell's layered texture is a direct imprint of UY Scuti's pulsation history, a record of its long, slow breathing written into space. The same process explains the periodic enhancements in mass loss. Observed in other red supergiants, pulsation weakens the binding energy of the outer atmosphere, allowing more gas to escape, especially near the peaks of expansion. The variability also influences how astronomers measure the star. Because brightness and temperature change with phase, estimates of luminosity radius and effective temperature depend on when observations are made. Early distance estimates based on measurements taken during brighter phases likely overestimated the size. Later data averaged across multiple cycles produced smaller but more consistent results. Understanding these pulsations is therefore essential, not only for characterizing UY Scuti, but also for calibrating models of all massive variable stars. Observing the light curve over decades allows scientists to refine period and amplitude trace changes over time and search for signs of evolutionary drift. Slight lengthening or shortening of the period may indicate that the internal structure is changing as new fusion layers ignite within the core. The pulsations also reveal the star's sound. Although inaudible to human senses, pressure waves within the atmosphere correspond to frequencies that can be converted into sound in simulation. In this metaphorical sense, UY Scuti sings a deep, slow tone, a resonance with a period of nearly a year vibrating through volumes larger than the solar system. Each note carries the echo of energy flowing from the core to the surface. To astronomers, these vibrations are data. By modeling them, they perform a kind of stellar seismology, probing the internal structure through oscillations that cross millions of kilometers of plasma. The information they yield refines understanding of density, temperature, and composition far below the photosphere. Yet the most striking aspect of UY Scuti's variability is its serenity. Despite the immense energies involved, the transitions occur gradually, with no violence visible to the eye. Expansion and contraction unfold at a pace that matches the slow pulse of the galaxy itself. The star's light waxes and wanes as though breathing, maintaining a rhythm that has persisted for thousands of years and will continue until the final stages of collapse disrupt the pattern forever. For now, each pulsation is a reminder of equilibrium maintained in motion, a cycle of release and return heat, and gravity, light and shadow repeating across cosmic distances in the quiet heart of Scutum. Every moment UY Scuti releases part of itself into the surrounding galaxy. The slow but constant outflow of gas and dust forms a wind that carries heavy elements away from the star, enriching the interstellar medium with the raw ingredients for future worlds. Over the course of its lifetime as a red supergiant, this process has already removed several solar masses of material, transforming the space around it into a diffuse glowing shell. The matter leaving the star travels at only a few tens of kilometers per second, yet over thousands of years it fills a volume far greater than the entire solar system. Seen through infrared telescopes, this outflow appears as a faint envelope of warm dust and gas, softly illuminated by the radiation of the star itself. In visible light, the region is nearly invisible, hidden by the same dust that it produces, but in longer wavelengths, it shines steadily, a record of loss measured in heat. The composition of this expelled material reflects the star's internal chemistry. Helium, carbon, nitrogen, and oxygen dominate with trace amounts of magnesium, silicon, and iron. These elements were forged in nuclear reactions deep within the core, then transported upward through convection and ejected into space through the stellar wind. As the gas expands, it cools, allowing molecules to form. Oxygen-rich compounds condense into tiny silicate grains, while carbon binds with oxygen to form carbon monoxide and other simple molecules. These grains absorb starlight and re-emit it as infrared radiation, creating the glow that outlines the star's presence, even when its visible light is obscured. Each grain represents atoms that once participated in nuclear fusion, now drifting freely through space, destined eventually to mix with interstellar clouds and contribute to the formation of new stars and planets. The rate of mass loss varies with the star's pulsation cycle. During periods of expansion, when surface gravity weakens, radiation pressure more easily drives material outward. At contraction, the flow slows. Over centuries, this modulation produces alternating shells of denser and thinner gas, which later appear as rings or arcs in infrared images. Such structures trace the rhythm of UY Scuti's long-term variability, mapping centuries of its history. The expanding shells move outward until they merge with the ambient interstellar medium, blending into the background of the Milky Way. Although faint, they contain immense quantities of matter enough to seed thousands of future planetary systems. The gradual dispersal of this material exemplifies the role of massive stars as engines of galactic renewal. In the region immediately surrounding the star, the outflow is dense and warm, dominated by gas that is still partly ionized. Collisions between atoms excite infrared emission lines that allow astronomers to measure temperature and velocity. Farther out, where the density drops, the gas becomes neutral and cool, forming complex molecules such as water vapor, silicon monoxide, and sulfur compounds. These molecules radiate strongly at specific frequencies in the submillimeter range, making them accessible to instruments like the Atacama Large Millimeter Array. Observations of these emissions provide three-dimensional maps of motion within the outflow, revealing clumps, filaments, and slow vortices. They show that the wind is not perfectly symmetrical, but shaped by local variations in the star's surface and by its slow rotation. Some regions expel gas more efficiently, creating lobes or arcs that extend unevenly into space. Such asymmetry will later influence how the eventual supernova blast propagates through the surrounding medium. The physical process that propels this mass loss depends on radiation pressure acting upon dust grains. Once solid particles form near the star, photons from its intense radiation field strike them, imparting momentum. The dust in turn collides with gas atoms and drags them outward, coupling the two components into a unified flow. The efficiency of this mechanism depends on how much dust is present and on its composition. Silicate grains absorb and scatter light effectively, so even a small abundance can sustain a steady wind. Observations of UY Scuti's infrared spectrum confirm strong silicate features consistent with dust-driven outflow. The grains formed close to the star are soon carried away, where they gradually cool and grow by collecting atoms from the gas. Eventually they become part of the diffuse interstellar dust that permeates the Milky Way. The cumulative impact of this outflow extends far beyond the star's immediate environment. The matter lost by UY Scuti joins the collective flow of material from thousands of other red supergiants and massive stars, forming the interstellar gas reservoirs from which future generations of stars are born. This cycle of enrichment underlies the chemical evolution of galaxies. The carbon in living organisms, the oxygen in planetary atmospheres, and the silicon in rocky crusts all originated in stars like this one. When UY Scuti finally ends its life in a supernova, the explosion will scatter even heavier elements, iron, nickel, and cobalt, into space, completing the contribution begun by its stellar wind. In this sense, the current mass loss is both a conclusion and a prelude, the final quiet release before the violent dispersal to come. From a physical perspective, the interaction between the outflow and the surrounding medium creates layers of complexity, As the wind expands, it encounters the slower material ejected in previous cycles, producing shocks that heat the gas and trigger chemical reactions. These shocks generate emission lines in the infrared and radio bands that reveal the density and velocity structure of the shell. Over time, the outermost layers cool and mix with the interstellar environment, while new material continues to emerge from the star, replacing what was lost. The process resembles a slow tide, an endless exchange between star and galaxy. Despite the vast scale, the governing equations remain simple momentum, conservation, radiative transfer, and thermal balance. Yet their outcome, a glowing nebula of dust and gas many billions of kilometers across, is one of the most graceful phenomena in the sky. In this flow, even small fluctuations matter. Variations in the star's magnetic field or surface temperature can create localized surges in mass loss, producing plumes that extend unevenly from the star. Observations suggest that such plumes may rotate slowly as the star turns, forming spiral patterns within the dust shell. These spirals trace the geometry of the star's motion through its own outflow, faint records of internal dynamics written on a galactic canvas. The outer edges of these structures mark the boundary where the wind slows and merges with the surrounding gas of the scutum arm, enriching it with heavy elements. This is the region where the personal history of UY Scuti merges with that of the Milky Way itself. Every atom in this outflow will one day participate in a new form. Some will condense into cold molecular clouds, others will join the birth of new stars, and still others may find themselves within planets orbiting distant suns. The hydrogen expelled today will combine with dust to form water in a future world. The carbon may become part of organic molecules. The silicon may harden into stone. The timescales are immense, but the transformation is certain. Through this slow diffusion of material, UY Scuti ensures that its existence continues beyond its own death, dispersed through the galaxy it helped build. For astronomers observing from Earth, the evidence of this continual loss is both scientific and poetic. Spectra show the fingerprints of molecules drifting away. Images reveal halos that widen decade by decade. Behind the calm red glow lies an immense exchange of matter and energy, silent yet relentless. UY Scuti is dissolving not in collapse but in surrender, giving itself back to the medium from which it once formed. The process is neither fast nor chaotic. It unfolds with the patience of stellar time. The light that reaches us tonight has already crossed the material it once belonged to, passing through the faint dust that the star released centuries ago. In that light resides a record of transformation, a journey from core to cosmos, from fusion to dust, from a single luminous sphere to the scattered substance of future stars. As UY Scuti continues to age, its internal balance grows increasingly unstable. The sequence of fusion reactions within its core progresses toward heavier and less efficient elements, and with each new stage the outward pressure that supports the star weakens relative to gravity. The red supergiant phase represents a pause before inevitable collapse, a long, luminous decline that will eventually end in a violent release of energy. Though the outer layers still radiate calmly across the constellation, Scutum, the core deep within, is changing rapidly on astronomical timescales. The helium burning that currently sustains equilibrium will give way to carbon fusion once the central temperature climbs high enough, around several 100 million degrees Celsius. That phase will last only a few thousand years, after which successively shorter stages of neon oxygen and silicon fusion will follow. Each reaction layer will ignite closer to the star's end, and the time between them will shrink until only days or hours separate one stage from the next. This acceleration marks the final approach to core collapse, when no further fusion can resist gravity. In these later epochs, UY Scuti will shed even more of its outer mass. The wind that now drifts gently outward will intensify as radiation pressure rises and the outer atmosphere expands further. The star may lose several solar masses of material in the final 100,000 years of its life, forming an ever-thickening circumstellar envelope. This envelope will become the stage upon which the supernova explosion will later play out. When the shock from the collapsing core races outward, it will meet this dense environment, producing a bright extended afterglow visible across the galaxy. The quiet outflow of the present thus lays the groundwork for the spectacle of the future. Yet even as theory outlines this sequence in detail, the precise moment and character of UY Scuti's ending remain uncertain. The boundary between a collapse that forms a neutron star and one that creates a black hole depends sensitively on the remaining core mass and rotation quantities that are still only roughly estimated. During the final fusion stages, the interior will become layered like an onion with shells of different elements, fusing simultaneously hydrogen outside helium, helium outside carbon, and so on down to silicon surrounding an inert iron core. Iron marks the limit of energy generation by fusion. Beyond it, nuclear reactions absorb rather than release energy. When the core becomes predominantly iron, no mechanism remains to support it against its own gravity. As pressure overwhelms thermal resistance, the core collapses inward at astonishing speed. In less than a second, matter will compress to nuclear density and electrons and protons will combine into neutrons, releasing a flood of neutrinos. This sudden implosion halts abruptly when the neutrons become incompressible, sending a shock wave outward through the surrounding layers. The shock will first stall, then revive as neutrinos deposit energy into it, transforming the quiet red supergiant into a supernova of enormous power. For a brief time, UY Scuti will rival the brightness of an entire galaxy, its light visible across thousands of light years, even through the dust of the Milky Way. If the remaining core after the explosion is between about 1.5 and 3 solar masses, it will stabilize as a neutron star, an object no larger than a city yet containing unimaginable density. If the mass is greater, gravity will overwhelm all forces and collapse the core into a black hole, a region where light itself cannot escape. In either case, the event will mark the end of the star that once illuminated Scutum. The debris ejected into space will expand for tens of thousands of years, forming a nebula enriched with heavy elements, iron, nickel, and others synthesized in the final seconds of the explosion. Over time, this debris will cool and mix with the interstellar medium, becoming part of the raw material for new stars and planets. Thus, even in death, UY Scuti will continue the cosmic cycle it has long sustained through its stellar wind. For now, the star remains stable enough to resist collapse. Observations show no signs of imminent explosion. The timescales involved, though short in cosmic terms, still span tens or hundreds of thousands of years. The apparent serenity of UY Scuti's red glow conceals the turmoil inside, where temperatures climb, fusion shells multiply, and the core contracts inexorably. The outer layers, inflated and tenuous, respond slowly to the changes below, maintaining the gentle luminosity that defines its present state. Astronomers monitoring its brightness and spectral lines find variations consistent with ongoing pulsation, but not yet with terminal instability. The path to supernova is gradual, a sequence of internal adjustments that culminate only after long epochs of seeming calm. The aftermath of such an explosion will reshape the surrounding region of the galaxy. The shock wave will sweep through the existing dust shell, compressing it into bright filaments of glowing gas. Radiation from the explosion will heat nearby clouds, possibly triggering the birth of new stars. The elements produced in the final moments, particularly iron and nickel, will scatter into space, contributing to the enrichment of the Scutum Centaurus arm. Within a few million years, that material will mix completely with the galactic medium, ensuring that atoms once part of UY Scuti become part of other stellar systems. Some may join the atmosphere of a new planet orbiting a young sun, carrying the memory of their origin in a star that lived and died long before. The transition from red supergiant to supernova is one of the most dramatic transformations known in nature, yet it is governed by simple principles: gravity compressing pressure, resisting energy, escaping. The same forces that have kept UY Scuti stable for millions of years will ultimately destroy it when equilibrium fails. The supernova will last only weeks, but its echoes and expanding gas in newly formed elements in the faint neutron star or black hole left behind will persist for eons. From Earth, that final flash will appear as a brief new point of light in Scutum, perhaps visible even in daylight, a celestial reminder of processes that shape galaxies. Between now and that event, the star will continue its slow evolution, pulsing gently, losing mass and shining across the Milky Way. Its end is not a sudden catastrophe waiting to happen, but the inevitable conclusion of thermodynamic balance. When the final collapse comes, it will not signify destruction in an absolute sense, but transformation, the conversion of gravitational energy into radiation of stable matter, into motion of one stellar phase into another. The death of a massive star like UY Scuti ensures the birth of countless others. Through that cycle, the galaxy renews itself, and the matter within it migrates from one form to the next. If human observers exist to witness the end, they will see the culmination of everything that defines the star today. The dust it has created, the shells it has released, the energy it has radiated, united in one luminous event. The light from that explosion will travel for thousands of years before reaching Earth, carrying with it the final chapter of a story that began when the Milky Way was younger. Until then, UY Scuti remains poised between stability and collapse, an immense aging star sustained by fusion yet preparing for its end. In every photon it emits, in every grain of dust it expels, it reveals the paradox of stellar life, that creation and destruction are not opposites, but phases of the same enduring process. The glow we see in Scutum tonight is both a signal of life and a prelude to death, a calm light that in time will give way to brilliance beyond imagination. From Earth, UY Scuti appears as a faint point within the crowded Milky Way, yet that tiny red glimmer has become a focus of continuous observation and refinement. The star's apparent modesty and brightness hides the fact that its light has travelled for thousands of years through layers of gas dust and magnetic fields to reach our instruments. Every photon that arrives carries the record of its long journey, encoded with details of temperature, velocity, and chemical composition. Through careful study of this light, astronomers have transformed UY Scuti from an anonymous entry in a variable star catalogue into one of the key markers for understanding stellar extremes. The history of that understanding reflects both technological progress and the patience of scientific observation. The first measurements of its variability, made with small telescopes and photographic plates in the mid-20th century, hinted that it was an unusual object. Later, infrared and radio observations revealed the surrounding dust, expanding the picture from a single star to a system interacting with its environment. Today, precision parallax data from the Gaia mission, combined with interferometric imaging and spectroscopy across the electromagnetic spectrum, have refined nearly every aspect of what is known about it. The act of observing a red supergiant like UY Scuti is as much about method as discovery. Because the star changes slowly, Research requires long-term monitoring that spans decades. Teams across the world contribute data from both professional observatories and amateur networks tracking its brightness and colour through every cycle. These records form time series that reveal subtle trends, shifts in pulsation period, changes in amplitude, and small alterations in spectral lines that indicate evolving surface conditions. The combination of ground-based telescopes and space observatories provides a nearly continuous view, allowing scientists to separate intrinsic variability from effects of dust and interstellar extinction. By comparing UY Scuti's light curve with those of similar red supergiants, researchers build statistical models linking brightness fluctuations to mass radius and mass loss rate. In this way, one star serves as a calibration point for many, anchoring our understanding of how the most massive stars age and die. Modern interferometers have brought the surface of UY Scuti into partial focus. Arrays of telescopes spread over kilometers of ground act as a single giant lens, resolving its disk into uneven patterns of light. These maps show that the surface is mottled with bright and dark regions, confirming theoretical predictions of vast convective cells. Tracking these features over time gives insight into how energy moves within the star and how localized outflows begin. Each observation adds detail to the portrait temperature map, showing gradients across the photosphere, polarization measurements, revealing magnetic alignment, and velocity maps tracing flows in the atmosphere. Although the distances involved are immense, the data are rich enough to model conditions as though the star were near. The resulting picture is not static but alive with motion, an enormous sphere of slowly shifting heat, each part in conversation with the rest. Spectroscopy remains the primary tool for deciphering this conversation. High-resolution spectra break the star's light into thousands of lines, each representing a specific atomic or molecular transition. By measuring their positions, astronomers determine the motion of different layers. By measuring their depth and width, they infer temperature and density. Repeated observations track how these lines shift during pulsation, providing a map of the star's breathing. The faint emission from surrounding gas reveals where molecules form, while absorption features from interstellar material chart the path between the star and Earth. Together, these datasets reconstruct the three-dimensional environment of UY Scuti with remarkable precision. From such work emerges an understanding not only of one star, but of the processes governing all massive stars at the edge of stability. Ongoing study extends beyond optical and infrared observation. Radio telescopes detect maser emission from molecules such as water and silicon monoxide in the outer envelope, signals that trace the motion of gas hundreds of astronomical units from the star. These masers act as natural amplifiers, producing bright, narrow lines that can be used to measure velocity fields with extraordinary accuracy. Their distribution changes slowly over time, revealing how the outflow evolves. Combined with infrared imagery, they form a bridge between the stellar surface and the expanding dust shell, showing the connection between inner pulsations and outer mass loss. At even higher energies, X-ray and ultraviolet observations search for signatures of shocks within the wind, though such emissions remain weak due to the star's cool surface. Each wavelength contributes a piece of the puzzle, demonstrating how multispectral astronomy allows a complete picture of phenomena once beyond human reach. The data gathered from UY Scuti also serve as tests for theoretical models. Computer simulations now reproduce the entire evolution of massive stars from birth to collapse, but the uncertainties in mass loss, convection, and mixing remain large. By comparing predictions of luminosity radius and chemical composition with actual measurements, scientists adjust the models until they match observation. The revised calculations then feed back into broader studies of galactic evolution, since the life cycles of massive stars control the rate at which heavy elements are returned to space. In this way, observing UY Scuti informs not only stellar physics, but the larger story of how galaxies recycle matter. Each improvement in distance or temperature measurement ripples outward through astrophysics, refining everything, from the interpretation of distant supernovae to estimates of cosmic chemical abundance. The human aspect of this study is one of persistence. Generations of observers have pointed instruments toward the same faint patch of sky, each adding a few more data points to an ever-growing archive. The tools have changed from glass plates to digital detectors, from isolated observatories to global networks. But the act of measurement remains constant, recording the light of a distant star and translating it into understanding. Amateur astronomers contribute observations of brightness variations that professionals later analyze statistically, linking the smallest backyard telescope to the largest space observatory in a shared pursuit of precision. The story of UY Scuti thus becomes a collaboration across time and technology, uniting countless eyes and instruments in the study of a single object. Despite the progress, many questions remain. The exact mechanism that controls the transition between stable pulsation and eruptive mass loss is still uncertain. The role of magnetic fields, the geometry of convection, and the precise threshold for core collapse all await clearer evidence. Each new generation of instruments, larger telescopes, more sensitive detectors and advanced space observatories promises to close these gaps. Upcoming infrared missions will image the inner dust shell at unprecedented resolution, while next-generation interferometers will map temperature variations across the photosphere. As technology extends vision further, UY Scuti will continue to serve as both subject and benchmark, a natural laboratory for observing processes that cannot be reproduced on Earth. Yet beyond its scientific value, the study of UY Scuti evokes a quiet reflection on scale and endurance. Light that left the star thousands of years ago is only now reaching us, carrying a message from a time when human civilization was in its infancy. By measuring that light, humanity participates in a dialogue across ages, reading the slow transformations of a celestial body whose lifespan dwarfs our own. The act of observation becomes an expression of curiosity, reaching outward through time, linking the brief moment of human awareness to the vast continuum of cosmic change. In the end, UY Scuti stands as both object and symbol, a real measurable star undergoing the final stages of stellar evolution, and a reminder of how knowledge accumulates through patience and collective effort. Its faint red light, captured in the sensitive eyes of telescopes, continues to teach how matter behaves under extremes of pressure and heat, how stars live and die, and how the universe renews itself. Long after the star has collapsed and dispersed, the data gathered today will remain a record of how humans looked upward and understood a giant that once defied their imagination. The calm light now shining from the constellation Scutum is not only the glow of a dying star, but a reflection of observation itself, an enduring signal that connects the vast with the minute, the distant with the momentary across the endless night of the Milky Way.